Okay, well, good afternoon. Welcome to Physics 2820, Lecture 12. Today we're going to talk about solving ordinary differential equations, building upon the work we've been doing in Taylor series, and seeing how to not integrate just integrals, but how to integrate ordinary differential equations. The basic idea of a lot of the problems we're solving is we can set up a physical system as a time derivative is given. That is, for lots of mechanical systems, the rate of change of something is represented by some formula, and that formula depends upon u and t. So one of the ways we've seen this is the rate of change of velocity. Velocity is the variable, depends upon the net force, because force acceleration depends upon the net force. We've seen this as other things, like the rate of change of the angle depends upon some formula based on what the current angle is and optionally what the current time is. Every one of these ordinary differential equations starts with some initial condition. So this is sort of a general way of writing lots of different types of ordinary differential equations. Sometimes these are called dynamical systems. We've already learned one way of solving these kind of ODEs, and that's using Euler's method. Euler's method can be derived by using a forward difference approximation. We talked last week about how to approximate derivatives numerically, and we said one way of doing it is to rewrite a derivative as its forward derivative. So that is to say that we can take a derivative and approximate it as y of t plus delta t minus y of t divided by delta t. If you look at this expression, we also know that this is accurate up to order of delta t. That is, the error is proportional to delta t. When you expand this out and rewrite this equation, what you can see is what the Euler method is giving us is an expression that says the next time step is equal to the current time step plus the derivative times that time step plus an error of order t squared. This equation is the exact same as what the Taylor series would be for y of t plus delta t up to order delta t. If you write down the Taylor series expansion for this thing, you will get these terms. So Euler's method reproduces a Taylor series up to order delta t. We call Euler's method a first order method because it reproduces Taylor series up to order delta t. What we can do is we can apply this idea to a different starting representation of a numerical derivative, and in that way derive a different numerical method. So if we think about instead the centered difference or a central difference, that is, we approximate a derivative as the centered difference of two things. It depends upon the previous time step and the next time step to figure out the derivative at the current time step. And one of the things we showed is this method has an error proportional to delta t squared. If you rewrite this expression so that you can do it as saying what delta t is as a function of the previous time steps, what you will see is this is the same, this can be rewritten in the following form. Now, in a central difference, what you're doing is comparing minus delta t to plus delta t. So if you just shift this around and think about the interval from t minus delta t up to t plus delta t, rewrite that so that this first bit right here, call that t, and call this t plus delta t. Effectively, what you're doing is you're changing the size of delta t by a factor of a half. You can rewrite this expression so it has the following structure. That is, the value of the function at the next time step equals the value of the function at the current time step plus the derivative of that function as evaluated at the midpoint all the way through. And that's just by going through the algebra from the top block to the second block. If you can estimate this derivative, or the right-hand side, which is the derivative, using something like an Euler's method, then what you can do is you can write down what the error would be in estimating the midpoint, and this is going to be accurate within second order. And then when you substitute that thing back into the original equation and you do some algebra, what you come up with is that the center difference leads to an algorithm which is the second order or the second term of the Taylor series. So we say that this rule, which is called the midpoint algorithm, is order delta t squared, or it's second order because it's accurate in the Taylor series up to that point. So the question from Kayla, does the O represent the same error as the first order method? Okay, so this notation of O, this is big O notation. This is saying that this term is something on the size of delta t squared. You can think of it as being a term which is, we don't know what the constant is, but it's a constant times delta squared. That's slightly different than the order of the method. That's something that's measuring the error associated with that term. We say that the method is second order because the first three terms of the midpoint method are the same as the first three terms of the Taylor series, up to and including order delta t squared. So the subtlety of what you want to call these two things is a bit different. The actual algebra of how I went from this first step up here down to this second step right here, I'm going to call that beyond the scope of the course. So don't dread too much of having to sit down and actually derive this. It can be done, and typically in a numerical analysis course, you would do a lot more of that. The way that we're going to apply it in this course is we're going to take a much more exploratory way. We could solve the equation, solve the system with a given delta t, shrink delta t by a factor of 2, and then ask the question, how much did the error reduce? And if it reduced by a factor of 4, 2 squared, then we would say it's a second order method. This is just a proof or a mathematical justification that the method is second order. What you do need to know is how to implement the method. So I could write it down like this, but let me write it down a slightly different way so it's much clearer what the numerical method actually is. What the midpoint algorithm is what you do is given an equation where you know what the right-hand side is. And this is important to remember. We are always solving an equation that looks like a derivative on the left-hand side is equal to some function, which could be anything, and that function is a function of the current y and the current t. This bit on the right-hand side is what I'm calling the right-hand side. I can evaluate this at any value y and any value t to figure out the slope at that point. So we've seen this kind of pictures before. If this is t, and I start at some point, okay, so let's call this, say, yi. Oh, no, that wouldn't be yi, would it? This would be ti. This would be yi. This is the known point. This is where we're starting the algorithm. And our goal is to try and figure out what it will be at the next time period. That is t plus delta t, right? The next step. We want to figure out what the value of this function will be. The way we do it in midpoint method is we start by evaluating what the slope of this line is at this point. We can figure out the slope because we know a formula for what the derivative is at any point and at any time. We call this slope S1. And then what you can do is you can use that slope to go up a half step. Okay, so this is like continuing this path on. And we're doing this up to a half step. So t plus delta t over 2. We can do that using a Euler half step. So just taking the derivative, going forward by a half time step, and we can figure out a new point. I'm calling this y star. And then what we can do is we can take that third point, or that middle point, and we can evaluate the slope at that point. We could say, okay, well, maybe at that point, that slope, that is the function evaluated with y star in this location, and t plus delta t over 2 in that location. You get a number. We're going to call that S2. And the idea of the midpoint method is to take that slope, take that exact same slope, carry it down here. It's the same slope. And then extend that slope to right there. This value is what we're going to call I plus 1. It's the value at ti plus 1. So this idea of using the slope in the middle of the interval is called the midpoint algorithm. So you can write it out in a fairly detailed way, like I've done right here. You could write it in a more compact way, right, like that, exactly the same algorithm, and it's showing you what to do. This algorithm does take 2 steps. You've got to evaluate the function twice, first time, second time, but there's a gain in the order of accuracy. So even though you're doubling the number of computations, the scheme is order delta t squared. We've seen this scheme before. This midpoint scheme is sometimes called the Euler-Richardson algorithm, and it can also be thought of as a second-order Runge-Kutta method. We've already seen the first-order Runge-Kutta method. That's Euler's method. You can think about a sequence of methods that have this idea of being, what is the rule with 1 step to make me go forward? What's the rule that makes me go 2 steps that gives me second order? What's the rule that makes that with 3 steps gives me third order? What's the rule with 4 steps that would give me a fourth order expression? That sequence of methods are called the family of Runge-Kutta methods. And so I'm going to talk about now the fourth order Runge-Kutta method to sort of give you an expression. But it goes on. There's a third and a fifth and a seventh, and you can come up with any of these kinds of methods. In a fourth order Runge-Kutta method, the algorithm is a little bit longer. So there is a fourth order Runge-Kutta method. Now, why would we want a method that has this degree of complexity? Because this is an order t, delta t to the 4th time step. That is, if you go through the effort to reduce the time step by a factor of 2, you're going to decrease the error by a factor of 16. You can prove this by writing out the Taylor series expansion of each and every one of these terms, carrying through the error, and if you just bring together the slopes of these 3 points and weight them appropriately, that will give you a Taylor series which is accurate up to the 4th power of delta t. So that's the way of proving this result. I want you to be able to understand the algorithm and just recognize that it's 4th order, which is why we call it a 4th order Runge-Kutta scheme. So let's go through what this method actually is and how we could go about implementing it. Again, the idea of all these problems is we are trying to figure out how to go from a current value of y at a current time step. So this is where we know where we're starting, and we're trying to figure out how to go from there to some future point in time, ti plus 1. The distance between these two things, that is what we mean by delta t. And we're trying to figure out what the next point is. We always know the slope. The whole idea of a dynamical system is at any point in space or time, you can calculate what the slope is. So what we do is we start by calculating the slope right at this point. We evaluate the function f of yi with yi ti's arguments, and we calculate the slope. And then what we're going to do is we're going to take a half step, like we've done before, and go up to the midpoint. So sometimes people call this ti plus a half, just to abuse the notation a bit. Go up to the half step, following along the slope of this guy. This point is the value of the function as evaluated at the half step. Then what we do is we evaluate the slope of the function at this step, which may have a different slope. We'll call that S2. Then use that slope, carry that slope down here, and use that one. I'll keep on using green. To come up with a new approximation of y I, 1/2. I'll put a star in here because it's a better guess. So notice that if you'd used the first slope, you would have misestimated where the slope was. But if you use this slope, this is a better estimate of what the value would actually be. Then what we do is we evaluate the slope at this third point. Okay, so let's evaluate the slope at this third point. Okay. We take that slope, we move him all the way back to the beginning, and the idea is the slopes are the same. We then use another step, an Euler full step, to get up to this point. We give this the value of y star, and we figure out the slope at this point. Okay, so lots of lines written down there, but that's what each and every one of these points is talking about. What you're doing is you're making either half steps or full steps with different slopes to come up with four different, where'd my pen go? S2. To come up with four different estimates of the slope. The slope here, 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 and here. And the idea is if you want to figure out the correct next value of yi, it's going to be some weighted average of this slope, this slope, this slope, and this slope. And if you do the Taylor series to come up with an algorithm that has the same order as the Taylor series components, the right linear combination of these things is to take a weighted average, which is 1/6 of this, 2/6 of this, 2/6 of this, and 1/6 of this. And if you do a weighted average of those slopes all the way together, what you will find out is you will come up with a slope, which is something in between all of them. And this is what you use to figure out the next point. The line says. It says figure out four slopes. Every one of those slopes is perfectly accurate because we know what the slope is. It's just where you're evaluating these functions. And that's the point, is these right-hand sides are being evaluated at yi, y1/2, y1/2 star, and y star. They're being evaluated at ti, ti plus t plus a half step, t plus a half time step, t plus a full time step. You're evaluating it 4 times. And if you do this, and if you were to go through the process of doing the Taylor series expansion, which will look a lot like what I did for the second order method, you will find that this is a order delta t to the 4th method. It's a 4th order method all the way through. Okay, so there's the drawing that you can do based on these sequence of steps. Partly though is, can you take this sequence of steps and not just sort of draw pictures, can you turn that into code? So let's clear this one up here and see if we can use these 3 algorithms to solve some differential equations. Again, our 3 algorithms are an Euler method, which is basically we evaluate the function at the left-hand side of interval and use that to figure out what it is on the right-hand side. A midpoint scheme, where we evaluate it at the left-hand side, do a half step, evaluate it in the middle, and then do a full step. And a 4th order scheme, where we evaluate on the left, evaluate it in the middle, come with a better estimation of the middle, evaluate it again, take a full step, evaluate at the right-hand side, and then take a weighted average of all 4 of those to figure out the next step. What would that look like in code? So to do this, we can start with a very simple ordinary differential equation. An equation we actually started the course off with. This is the same equation you would get with exponential decay or radioactive decay. And it's one where you know, basically from inspection, if nothing else, that the solution to this differential equation is an exponential function. If you're thinking about an equation which says dy dt, the derivative of y is equal to the minus of itself, this is a situation where we can use the tools of a mathematics course in ordinary differential equations to solve this, or we could just use inspection, come up with a function whose derivative is equal to minus of itself. Well, the function that does that is the function y equals some constant e to the minus t. That's the family of functions that satisfy this rule. If we add in the initial condition that when time is equal to 0, we can solve this for c and figure out that the exact solution to this problem must be y equals e to the minus t. That's an exact answer. And we can do that for some differential equations, but most of them we can't. But we can use this exact solution to understand how the error of these three methods, Euler method, second order Runge-Kutta, and fourth order Runge-Kutta, all compare. So what I'm going to do is I'm going to use this solution, and I'm going to evaluate this under these three methods. Okay, so in terms of a code, let's just do this at fairly low resolution so you can see the difference. I'm going to only consider going up to t equals 4, and I'm going to take fairly large time steps. These time steps are way too large for Euler method, but I want to show you that even though you're taking very large time steps, that the fourth order Runge-Kutta method works out just fine. In all these cases, one way of solving these kind of problems is to just come up with a range of values. Now you can do this by either trying to figure out how many steps it would be, or just using a NumPy array and directly pre-calculating what all the time intervals are. The T0, T1, T2, 3, 4, up to Tmax. We've already talked about that we can by hand, with pencil and paper, calculate the exact result all the way through. The Euler's method is a scheme where what you do is you evaluate the right-hand side of the function. And once again, the right-hand side of the function that we're evaluating, right? In this case, the f of y minus t, the right-hand side, it's a very simple function. It's just equal to minus y. It doesn't depend upon t at all. So we evaluate the right-hand side. It's equal to minus whatever y is. Use that slope, which I've called S1, to do a full Euler time step. And that sequence, if you repeat it again and again, that is Euler's method. The midpoint method, which is also known as RK2, which is also known as Euler-Richardson, right? Different names for the same algorithm all the way through, is to evaluate the slope at the beginning of the interval. So it starts the same way. You're going to use an Euler half step to come up with a new value of y, evaluate the slope at that midpoint, and then take a full step to come up with the answer. So that's the sequence for doing the midpoint method. What I'm doing in these algorithms is I'm starting by allocating an array, which is the right length to hold all the answers. And I'm always computing the next value in the sequence to figure out what it's going to go up to. There are other ways of doing this loop, but I want to focus on the algorithm. Okay, the one which we have not seen before is the fourth order Runge-Kutta method. So here we go for fourth order Runge-Kutta. You need to calculate the slope at the left-hand side of the interval. So you evaluate the function at the left-hand side of the interval. You do an Euler half step to get up to the middle position. Now, I don't need to call these variables y1 half and y1 half star. I could just call them y1, y2, y3, y4, just the first, second, third, fourth. I can use whatever names I want on the left-hand side. I evaluate that function at this midpoint. I take another Euler half step with that new slope. I evaluate the slope again. I take an Euler full step with that slope, and I evaluate the slope one last time. The full step then to get from the initial solution to the final solution is a weighted average of those four slopes altogether. That's the Runge-Kutta algorithm. Okay, so if I take all that together and remember to run some code, because I forgot the first cell, we've now solved all these ones. What's interesting, of course, is to look at how they compare to each other. So because I've solved them all, I can make a plot of the exact solution, the Euler's method, the midpoint method, or the fourth order Runge-Kutta method. And here we go. The black line is the exact mathematical answer. It's computed analytically, it's exact, even though we don't have very sharp resolution. But for every point on this sky, the green dots, or rather the dots which are underneath here, they're perfect. Notice that the Euler point is underestimating the derivative. So if you use the Euler algorithm for a given value of delta t, and in this case the delta t is a half, you are seriously underestimating the value of the function. If you use Euler-Richardson for the same step size, the error is a lot better. It's a lot smaller, but it's overestimating it all the way through. If we use Runge-Kutta 4, even though it's a more complicated algorithm, you can see that as far as the scale of this graph is concerned, the Runge-Kutta method is going right through it. Now, if we'd zoomed into that green dot, you would see a discrepancy between the exact answer and the Euler method. But the point is, for the same size time step, observe how much better the fourth order method is working compared to a first order or a second order method. Okay, let's do this again with a different differential equation. Here is a slightly more complicated differential equation. We want to solve the following ODE numerically. Now you might go, well, what does this have to do with physics? This is just a generic dynamical system, but this thing on the right might represent a spring mass system. So potentially this might be the restoring force, right? So how much has been pulled back by, and this could be some forcing term that we're adding to it. This could be something that we derive from a physical system. In this particular case, the right-hand side is whatever the function is on the right-hand side. So it happens to be, in this case, -2 times y times 3 times e to the -4 times t. Okay, so that's what the right-hand side is. This is a function which you can, or one can, and especially if you've taken a course in ordinary differential equations, you will learn methods to solve this kind of sign of equation. I think it can be solved with an integrating factor. If you were to do that, you can come up with an exact solution. Not all equations written as differential equations have exact solutions. They're not things that we can always do, but we can for this example. Rather than having to code up this function again and again and again, it is easier if we define a standalone function which represents the right-hand side, so that I don't make any mistakes copying the -2 times 3 times -4. We can just do this once and create a new function called f of y comma t that runs this. Then the three algorithms are as follows. Euler's method is evaluate the function at the left-hand side, take a full Euler step. The midpoint ski is evaluate the function twice. The Runge-Kutta method is to evaluate the function 1, 2, 3, 4 times. And if you run that code, you can compare those four. And again, using this fairly large time step, you can see that the Euler method actually really overshoots it and then starts to undershoot it, depending on this curve. The midpoint method is actually worse than the Euler method for this particular time step. So just going to a better method doesn't necessarily mean it's going to be less error. The error has to do with the way that these methods converge as you shrink the time step. But the Runge cutoff method, you can see that, at least on the scale we've given it, it appears that the Runge cutoff method is going right through the exact solution all the way along. I've only evaluated the exact solution at these discrete points. I think the real solution does something like this. It goes up and down and around. It has a loop. I think if we were to actually plot it, we'd find that this is more the real solution. Something that looks like that all the way through. But the Runge cutoff method's a lot better. Here is an advantage for doing this kind of problem, or doing it this way, is now that we've separated out what the function is from how to run the algorithm, I can now very quickly just change this right-hand side, and this code will work exactly the same way without me having to make any changes at all. I'll draw your attention, as I started this lecture off with, for your assignment number 4, what I'm going to have you do is I'm going to have you solve this differential equation using the midpoint scheme. I'm giving you some code that solves the midpoint scheme for any right-hand side. Here's a particular right-hand side. Solve it. Now, this question is actually going to get you to implement a brand new algorithm, something else, where I've given you the equations, and I want you to write a new solver, a new loop that solves that same system of equations. That other method is called a predictor-corrector equation. Okay, Kayla's noticed something in the solution. She's saying, isn't the function minus 2 times y plus 3 times e to the minus 4t? The function is indeed minus 2 times y plus 3 times e to the minus 4t. Kayla, do you have a comment or a question about that? I agree with you. Were you confused with the exact solution? Oh, earlier I had written. You mean when I was trying to differentiate between those two things, writing with a mouse? Perhaps. It's entirely possible that I wrote this when I should have written that. Okay. The code, which is why we wrote the code. So these chicken scratches is, I apologize. You're totally right. It is 3 times e to the minus 4t. That's what we wrote in the code. This is why we typeset mathematics, because handwritten mathematics is tricky to read. That is for sure. I like to typeset everything. Okay. So the point being, you now have a technique or a method to solve lots of systems. If you know the right-hand side, there is a midpoint scheme. There's a Runge cutoff scheme. On assignment number 4, I'd like you to implement a brand new algorithm. It's slightly different. It's another second-order method. It just has a different algorithm. So please implement that and compare the two. Okay, we do this. We introduce these dynamical systems, these problems which are written as dy dt is equal to the right-hand side in a computational mechanics course, in a computational physics course, because many, many physical systems reduce themselves down to the mathematical problem given as an ordinary differential equation. Let me show you 3 different differential equations that we've seen recently. Here are oh, wait a second. Yeah, here we go. Here are 3 systems which we've seen recently. The problem of a projectile motion with quadratic air drag, the problem of a proton moving in a magnetic field, and the problem of a Duffing oscillator. These are the 3 dynamical problems I put on the first test. They all are of the form, the derivative of something is equal to some function of all the variables. For the first 2 problems, t does not appear on the right-hand side at all. There's no time dependence. But for the Duffing oscillator, it's a function of the variables, the v, the x is repeated twice, and time. So what you can do is you can think about all three of these problems as being a system of first-order differential equations where the derivatives are all on the left-hand side, and there's some function of all the variables and optionally time on the right-hand side. Every one of these three problems can be thought about in a more abstract way as a system of equations that look like this. Doesn't matter what dynamical system I'm looking at. They're just a bunch of derivatives of all the variables of interest: position, velocities, accelerations, charges, masses, densities, whatever you're measuring in your physical system. And then some equation of all of the variables in your system, and optionally time. Time doesn't have to be in there, but it could be, that give you what the right-hand side is. This whole thing together is called a dynamical system. Now, for every one of these types of problems, it may have different variables, right? So in the first case, for projectile motion, the variables are x, y, vx, and vy. For a proton spinning in a magnetic field, you might have three position velocities and three positions, indices, and three velocity components. For a Duffing oscillator, maybe we only have one position and one velocity. But in general, you've got this set of variables that depend upon some function of the current positions and the current time. Right? So in particular, for the Duffing oscillator, this first equation is f1 of x comma v comma t is exactly equal to v. Doesn't depend upon x or t at all. The equation, which is the derivative of v prime, is more complicated. It's a constant times v minus another constant times x plus another constant times x squared cubed plus another constant times the cosine of another constant times t. This delta, alpha, beta, gamma, and omega are called parameters of this model. They're not really variables in the same sense that x, y, vx, and vy are. It's not something we need to figure out. We are given those parameters as something about the problem. So the strength of a spring, the mass of a particle, the amount of charge, the damping coefficient, these are all parameters of the problem. What we can do is we can abstract this system of equations and bring in the idea of vectors to write all of this as a much more compact notation. Do you see how effectively we have x comma y comma vx comma vy, and that's repeated again and again? Let's introduce a vector that I'm going to call the state vector. That's all of the variables brought together. So this is a vector, as in something that has four components. It can be written as a column vector or a row vector, it doesn't matter. And the idea is this is an ordered pair that shows you the current state of the system, all of its variables. For notation purposes, what it means is whenever we see the symbol S arrow, that represents all four of these variables together. So the system of equation can be written more compactly as x prime equals f1 of the state vector and time. V prime is equal to f2 and the state vector and time. We can continue to use this idea of vectors to make this even more compact. And we can introduce the idea of vector-valued function. So f1 depends upon a vector. F vector, capital F, itself is a vector. So the idea here is the output of this function itself is a vector where its components are little f1, little f2, little f3, and so on. So this is a function which takes in a vector, S vector, and time, and gives it back out a vector. So it's a vector in, vector out. It's a vector-valued function. Okay, once we have introduced that idea of a vector-valued function and a state function, we're able to take the entire system of equations. Rather than having to write all of this down, we could write it more compactly as, right, like that. That is, the derivative of the state vector is equal to this vector valued function of the state vector. Now, the way you take the derivatives of a vector is you just take the derivative of each component of the vector, but this is a generalized way of talking about any dynamical system we could write down. Just tell me what the capital F vector is, function, tell me what the state is, and I know the equation. What about parameters? How do I somehow get in the idea of alpha, beta, gamma, omega, m, q, b, c, whatever into the equation? Well, sometimes you can talk about that itself being a vector of parameters. When you have a function which depends upon things that are like parameters but not true like variables, one notation that is sometimes used is to put a semicolon into it. And that is to say this function depends upon these three things in their domain, and these things are parameters of the function. And one notation that you sometimes see is a semicolon to indicate the difference. What we can do is take just these things on the right-hand side, create yet another vector called a parameter vector, and then we can write each function as dependent upon the state and the time, and perhaps some parameters. And this becomes the most general way of writing down this problem. One more thing. To solve a dynamical system, you always need an initial state. You need something to integrate from. So what we can do is we can talk about the initial state and construct something we're going to call an initial state vector. For every value of the function, we can imagine knowing what it is at time equals 0, take all of those values together and call that the initial state vector. So the complete problem of every and all of the dynamical systems, all the mechanical problems we've covered so far in this course, can always be written in this general form. The derivative of the state vector is given by some known function of the state vector and time, and optionally some parameters, where we are given some initial state. Each one of these parameters is laid out, and if you just know how to solve these things, you can solve lots of different physical problems. One of the things we'd like to do is to decouple the physics of the problem, setting up the system equations, from the implementation of the numerical model we're going to use to solve it. So what we can do is, in the same way that we had the example above, where we defined a special Python function for the right-hand side and then wrote a generic solver that worked for any function, we can do that as well for these generalized systems of equations of motion. So to introduce this idea, I'm going to go back to the simplest numerical method we know, that is the Euler method, and write an Euler stepper. That is a function which takes any generic right-hand side and steps through it in time according to the Euler method to give me back the state vector as it evolves in time. The way we can do that is we can write a function that I'm going to call Euler stepper because it's a stepper code that takes in as arguments a function. Now I'm writing this in the comments as the default just to make it clear, but it's some function of an S and a T and a P. What we're going to pass in as the first argument is a function, some function that's going to explain the state of the system. We're going to pass in a vector for the initial state, an initial time, a parameters vector, and then because we always need this idea of a time step and a max time, we'll pass those in as well. But this is completely general for any dynamical systems. What this code does is it's solving the dynamical system. The derivative of S is equal to f of s comma t with the optional parameter vectors p. And the point is S and P are vectors. There's some sort of structure that contains all these numbers back. Now, we could write these things with dictionaries or with pandas series. And in preparing this lecture, I tried that. The performance isn't very good. Python works much better if you're passing around numerical arrays as opposed to more complex data structures. So I'm going to do this all using numerical vectors. The basic algorithm is to start by given some vector, define it as a NumPy array. The advantage of being a NumPy array is Python's able to deal with these things a lot quicker. Loop through your data while t is less than some tmax. Every time we want to report back to the original function what the current state of the state is, what I'm going to do is I'm going to make a copy of those variables, turn the numbers into a list, and then tack on the time so that we have the state and the current time all together. But in the body of the loop, we're going to use this function that we're going to pass in. We don't yet know what capital F is. It's some function to be determined that will take in the vector s and return back out the vector ds that is the slopes or the derivatives of every state. Then what you can write is the state is equal to the old state plus the slope times delta t and update delta t. This is a generic Eulerian stepper all the way through. So if I apply this to the problem of a projectile motion with air drag, this is the system of equations. Here is an example of a right-hand side equation, a capital F function. It's something that takes in as an argument an array of state, the four variables that we're defining. Our state vector is x, comma y, comma vx, comma vy. So what I can do is take that array and pull out each one of its four values to give them some names. I can take the vector p, pull out each value I want. So for this particular problem, I need to care about gravity, drag coefficients, and masses. Then go and calculate something specific about this physical problem. I might need to calculate the speed from the velocity components. And then what I do is I figure out what the right-hand side of each one of these equations are and encode those as the derivatives. So what's the derivative of x? Vx. What's the derivative of y? Vy. What's the derivative of Vx? Well, it's going to be proportional to the drag. What's the derivative of Vy? The acceleration due to gravity and the vertical acceleration due to drag. Take those things, wrap them up as an array, and pass them back. Those two components separate out the numerical method of the Eulerian stepper from the physical problem that we might be solving, like projectile motion. We can put that all together into an application. We can say, okay, I want to do a projectile app kind of program. I need some parameters. I might still need a time step. I might need some initial conditions. I might need some parameters. But what I'm going to do is I'm going to take those things and bundle them all together is a state vector. And I'm going to bundle all the parameters together. And I'm going to pass in this stepper some function which I've defined. So f projectile, I've defined that up here. It's some function of s, t, and p. Include a state vector, include a parameters vector, include time and dt, and then I can create a data frame out of this. The only one subtlety here is because I'm just passing arrays back and forth and not dictionaries. It doesn't have any names for these things, just calling them the first variable, the second variable, the third variable. So what I can do is when I create this data frame object, I can actually give it some names. I can say the columns are the x, y, vx, and vy. The stepper doesn't actually know the names of any of the variables. It's just the first variable, the second variable, the third variable, the fourth variable. It's not thinking. It doesn't know that one means position and one means velocity. It's just the first, second, third, and fourth. So that scheme allows me to then solve projectile motion. So this is something that's not quite a parabola because an object with an initial velocity towards the right and sinking under drag, it's going to have this sort of flat down sort of shape. There's a question in the chat that asks, what is the purpose of lambda in the arguments given to the stepper? Whenever we're defining a function, anything here on the right are defaults, things that we haven't given it just to make it work. And what I'm doing is I'm defining a default value for f, which is a simple function. And the function is, given the vector s, t, and the vector p, give back s. This is a default, so that if I didn't put in any equations. If I didn't provide a function, the system would go and just choose this as the default. Why I do this is because it makes it clear for someone who's going to use this function that this first parameter has to be some function. It has to be something which takes in an S, a T, and a P and gives back something. And the something happens to be the right-hand side. But it's a way of indicating to a reader of the code what kind of computational Python thing I want to put here. And what I want to put here is a function. So it's a function that takes in three things and gives one thing back out. Well, my function, fProjectile, takes in three things and gives one thing back out. That's what it does. So the purpose is there of the Lambda is for better readability of the code. Let's take that idea and apply it to a different physical problem. Okay, so here's a completely different physical problem. This is the problem of a proton in a magnetic field. So this is the one on the term test where if you have a proton which is fired in a direction where it's moving perpendicular to a magnetic field, then what's going to happen is that proton is going to trace out a spiral shape or a helix all the way through. You can come up with these equations of motion by knowing about how a charged particle behaves in a magnetic field, right? Something you could do from either 1051, what we learned in 1051, and of course this first bit is just saying the derivatives of the positions are equal to velocities. As a right-hand side or dynamical system, we want to code up the right-hand side all the way through. In this problem, the state vector is x, y, z, vx, vy, vz. The parameters are q, b, m, comma, equals p. And the right-hand side is the derivative of x, derivative of y, derivative of z, derivative of vx, derivative of vy, derivative of vz. And then it returns back that whole thing as a vector. If we want to use that function, then we can define some initial variables, come up with a state vector, come up with a parameter vector, and use the same stepper all the way through to solve for it. So what you're going to get if you plot it is you're going to get a spiral, right, going all the way through. Now the thing is when you're writing these codes, because we're not using dictionaries, things with names, the order of the variables is critically important. As you're writing these things, when we actually go to implement fproton, I'm assuming that the order of the variables are always x, comma, y, comma, z, comma, vx, comma, vy, comma, vz. That means that whenever I unpack it or pack it, I have to respect that order. If I was to take this function and have this function, but then choose for some bizarre reason that I wanted to start my step function like that, I start my state function like this, where I said, I'll do x, then vx, and y, then vy, then z, vn. That would be bad, okay? Because I need to know the order in which I'm doing things. This method of communicating functions back and forth are representing the state vectors by their relative positions, first, second, third, fourth. You can't just change the order any way you want. You need to be consistent all the way through the order in which you're unpacking the state vector, packing the state vector, and naming the columns. Be consistent and you won't have any problems. But if you mess this up, then it's not going to work. So I'm going to undo all of that because that's bad. Likewise, the order in which you're packing up the parameters needs to be the same order in which you unpack them. If you go along and you swap the order, so now I'm talking about as being q comma m comma b, not q comma b comma m, that won't work. So the order is pretty important all the way through. Okay. Now, if we look at this algorithm, you'll see that this is a spiral. There's a problem. You might recall from either the test or from first year physics that a proton in a magnetic field, the magnetic field's not doing any work on the proton. It should not be increasing in its radius. It should just be traced in a perfect spiral. Part of the problem is the Euclid method is not conserving any energy. So what we can do is we can take the exact same dynamical problem, the same physics, and swap out the numerical solver. So notice that we've already written up our right-hand side. We're not going to change that. We're going to use exactly the same right-hand side and not touch it. But now I could write an application that uses a midpoint stepper. And again, what this is a completely abstracted numerical method that takes in the same arguments. It takes in a generic function, an initial state, initial time, and it solves it not using the Euler method, but using the midpoint method, which is why I'm calling it midpoint stepper. What you need to do is compute the slope at the left-hand side of the interval, update the slope in the midpoint, compute the slope in the midpoint, and then update the final state. So this is the sequence that every midpoint algorithm needs to do. By making one change to the application, namely taking that proton application, and I just copy and pasted it, and I changed one word. The only change I made was I replaced this word. It used to say Euler stepper, and I replaced it with midpoint stepper. That one change allows me to change the numerical method. And the point is, now you can start to explore, for the same physical problem, how different numerical methods may affect the solution. You may go, I don't know what numerical method I want to use. I want to try a few different ones. It's very easy to do. You've separated out the physics of the problem from the numerical method, and all you need to do is change what this function is. Now, some of you might be thinking, well, that's sort of good, but didn't he just have to copy and paste that entire function? I got one copy of it and two copies of it. And some of you may have talked to me, and I've talked about the DRY principle, the do not repeat yourself principle. It's bad programming form to have code that you've duplicated. So here's how I would tend to write that actual function. I would write the proton app like the following. I would set it up so that the proton app took as a stepper a default. This is going to be a variable inside the function. If you don't tell it anything, it's just going to take an Eulerian stepper. And down here, it's passing in stepper. So when you call this function, if you don't provide an argument, it's just going to take Euler stepper and put it right here. But what you can do is you can replace this with any numerical algorithm you want. So I can run that, and now what I can do is run the proton application with an Eulerian stepper, run it with a midpoint stepper, side by side right away, and compare the two. And be like, oh, that's the difference between the Eulerian stepper and the midpoint stepper all the way through. I think the next step in this sequence of thoughts, and we either could do it now or we'll do it on Thursday, I guess, is you go, okay, well, that's fun and interesting. What would I need to do so that this code would work, right? How can I make it so that this code would work so that I can compare three different models? I'd obviously want to plot out the data for those three. Go RK4, RK4. Okay, this is Runge-Kutta method 4, right? Now, if I was to run this code, I'm expecting to see an error, and the error is you haven't yet told me what the Runge-Kutta number 4 is. So we want to be able to write one. Well, how would we write one? What I would probably do is I would go and take an existing stepper code, like midpoint stepper. I would just copy and paste the whole thing. Give it the name of an RK4 stepper. Its basic structure is the same. It's going to take in a state vector. It's going to do some stuff to it. Before we make any changes at all, we've copy and pasted some code. Let's just make sure our driving program still works. Now it's working correctly. You're seeing Euler, midpoint, RK4. I've used the same color blue in 2 types. Let's make that a green. Okay. They're right on top of each other because all I did was copy and pasted the algorithm. We have to be a bit cleaner if we want to look at a Runge-Kutta-4 method. We actually have to implement that right here. So we can do that. We can try and figure out what lines of code should go here to implement a Runge-Kutta-4 algorithm. And my suggestion for doing that is not to read and write, but to find a correct working implementation of the Runge-Kutta-4 algorithm. RK4 method. I'm going to copy that and bring that down. Okay. And what I'll do is I'll just put it right here. Okay. And even if you just sort of left it in here, commented out, that might be something you could use to figure out how to write your version of the program or your revised version of the program, something that respected Runge-Kutta version 5. Okay, so what are the steps? Well, we need to first estimate the derivative at the current point. That is the starting state all the way through. Once we have that current point, what we need to do is we need to evaluate the state at a half step away from that. Oh, I got to be careful here. Careful. Careful. Okay, so there's a complexity already. I'm noticing that I've changed notations. In the 1D case, I was using S for slope, but now I'm using S for state, right? So we got to be a bit careful, make sure we don't confuse ourselves. So this is the derivative at that point. The state is equal to the original state plus the slope at that point. Then what we want to do is we want to evaluate the slope at this new state, but at a half time step. Okay, that sounds good. Then I need to evaluate the function at this new state. So what I'm going to do is I'm going to take ds2, and I'm going to call that the second state all the way through. So this idea is being implemented by this piece of code. Let's keep on going. To figure out the third slope, what I'm going to do is I'm going to evaluate the function a third time. This is my third slope. I'm evaluating it at this point at the mid-time step. I'm going to evaluate my function a big step, an Euler full step. How do I do that? Well, I'm going to take that slope, the original state, add that third state and do a full time step. Finally, I'm going to evaluate this point right here at one full time step forward. And I've got to figure out what that would be. So I'm evaluating this at the right-hand side of the interval, one full time step. And then to figure out the final state all the way through, what I do is I take the current state and I add to it the weighted average of all these guys. The first slope, ds1, ds2, ds3, ds4, and I weight them by the time step. Okay, so now we take a stab at this and we read through it carefully to make sure we haven't made any mistakes. I know the time step that's given to me. I'm evaluating the slope at the left-hand side. I'm evaluating a new state at the half point. I'm evaluating the slope in the midpoint. Oh, I lost a 2. I'm evaluating the new state at the midpoint. I'm evaluating the slope at this new midpoint. I'm evaluating the state at the right-hand side of the interval, evaluating the slope at the right-hand side of the interval, and I'm making a Eulerian full step with this as the weighted average slope all the way through. Hopefully, if I now go back and run this, it's going to work. Fantastic. Now, what's tricky to see, of course, is you're not seeing the difference between RK4 and midpoint. This might be one where you want to plot the data zooming in all the way through, or maybe we're going to do it for a lot larger value of dt. But there we go. We have now written up and coded a generic RK4 stepper. The only other way I would improve this or tackle this now is maybe we would take this algorithm and say, okay, I've now coded up Runge-Kutta version 4, and maybe I want to use it to solve the Duffing oscillator, this problem right here. So I've decoupled how to solve these problems from how to formulate these problems. That means that if someone was to come along and invent a brand new numerical method, you could just use it directly on your existing problem all the way through. And I think that's a good place to stop for today. On Thursday, I'll introduce you to some other numerical solvers that are implemented as black boxes. That is code that you don't need to know exactly how it works on the inside, but they behave like this, something that does steps all the way through the code. And so you can compare the performance of a midpoint stepper to an RK4 stepper to some other stepper. And the name in numerical analysis is these are called integrators. Something that solves a numerical, an ODE is called an integrator. A new kind of integrator that might work better all the way through. Okay, so that's a fair bit of content because we've talked about midpoint and Runge-Kutta, and we've talked about this abstraction of going all the way through. This gets us to the end of sort of the lecture proper. We'll dive into lab number 4. I'm hoping lab number 4 is not too bad. I'm going to encourage you to take a look at assignment number 4 as soon as possible, which might be right now for a few minutes, because I think you will be able to do this problem right away, as in now. Fresh in your mind, you might just want to get it done. This question about the Simpson's rule is just taking what we had already done in the previous lecture and applying it again. So don't leave these assignments questions to Sunday afternoon. They're things that you could plow through either right now, tonight, tomorrow, the next day. But if you're around for Tuesday's lab, we'll get started on this right at 3:30. And we're going to talk about numerical differentiation and integration. Are there any other questions about this lecture before I sign off for today and we begin the lab, or take a break and then begin the lab? Okay. Not hearing or seeing anything. I'll stop the recording for now and post this up on YouTube, and we'll go into the lab. Thank you very much.